not an empirical application, but at least I will talk about how to apply these methods. So the title of the talk is Separable Matching. Seems to be bizarre, the title, because if you match people, why do you want to do the reverse and separate them? But I'll explain what that really means. And this is work in several papers with Alfred Galichon, who is at Choo and Siow. So basically, if you look back 20 years ago, and some of you were not even born, but, the idea was that estimating matching models was really hard, taking them to the data. So one way is you just do brute force. You can always do that in statistics or econometrics. You have a model, you can simulate it. You do a lot of simulations, and then you compare them to what you observe, and you try to minimize the distance between the two. For matching models, it's not very convenient, and also it's not the modern norm in econometrics, which is when you get an estimate, you have to explain where it comes from. What are the hypotheses? If you just do this kind of brute force thing, you don't have a lot of ideas about where it comes. So another way, which was not used so much in statistics and econometrics, you just regress things like the number of matches between highly educated people and not educated people, and you regress it on various characteristics. You get estimates, you always get estimates from a linear regression. The problem is, what do they mean? And I'm going to show you an example that shows that in general, they don't mean anything, but there's been a lot of this work being done in other social sciences, let's say. So the new thing is that it's become really easy to estimate matching models. And when I mean really easy, is that sometimes all you have to do is run regressions, but justified regressions, or at least I will try to justify them, at least if you focus on matching markets that have transferable utility. So this works also for imperfectly transferable utility, but the whole talk is going to be about perfectly transferable utility. And once you make an assumption on the way unobserved heterogeneity, which is the econometrician term for stuff you do not observe, but that the agents observe in the market when they make their decision. So just think of them as error terms. We have to restrict the form that they take in the generation of utilities, and then you get things that are really easy to do. So how easy? That's a very good question. So if you take, for instance, the most popular application of matching models with perfectly transferable utility, and the iconic model is the Shapley, Shubik, Becker, Koopmans model, in which you have a marriage market. So the marriage market is fairly specific. It's one-to-one. So typically, we don't have polygamy or polyandry. And traditionally, at least, it was bipartite. So there is one subpopulation, we call them men, one subpopulation, we call them women, and we take one from each. So in this kind of application, so the pioneering paper in the empirical literature is Choo and Siow in 2006. So let me introduce some notation. We have observed characteristics of a man. So a man is them, a woman is W. The observed characteristics are going to be discrete. Again, that can be extended, but it's simpler here to do it this way. And for the woman, they're Y. And of course, that does not exhaust the list of characteristics that matters to the partner. I don't observe hair color, for instance, usually, but probably hair color is important. I don't observe religion. Religion will be more or less important in different societies. But these are the ones that I observe as the econometrician, and they observe more. So the Choo and Siow model says, if you match a man of characteristic X and a woman of characteristic Y, so W as Y, M as X, there is something that only depends on their observed characteristic, and I'm making it linear. And then there are these two random terms. So these two random terms, notice that they interact M and Y, so the unobserved characteristics potentially on one side and the observed characteristic on the other side. Same here, but what we don't have is the term MW. MW would be an interaction between the unobserved characteristics on both sides, and you're going to see the benefits of including it. The costs are obvious. Sometimes they might be important. If you look at data from India, for instance, maybe it's really important to have religion or caste, which you may not have in the data. And the other reason is that we don't really know how to model these things. They are unobserved to us, so if you put an epsilon MW or UMW, you're going to have to make a modeling decision, and it's not clear which way you're going to go. So we start with that, and in their model, these epsilon and eta, they're IID, they all have the same distribution. They're type 1 extreme values, which just means you're going to get formulas that look like exponential divided by sum of exponential. So, and again, we only observe X and Y, so all we can get from the data is put people in cells, X and Y cells, and count the number of marriages within any cell. Okay, so that's what we have. You could have data on transfers. It doesn't work so well for the marriage market and so on. I'm just going to assume we have no additional data. So here, what would you do brute force? You would pick values for the parameters you want to estimate, the betas. Then you would draw epsilon and eta for everyone in the population. Then you would solve for the optimal assignment. Then you would aggregate to get this mu xy, which depends on beta, and then you would compare with the observed mu hat and xy. And that it's possible to do. And then you iterate, of course, until you get a beta for which these two, the 1 in 4 and the 1 in 5, are really close. So it does give estimates that have good properties, but it's pretty laborious, actually. And also, it doesn't really tell you what drives identification and what makes your estimates credible. Okay, so the other three directions would just say, I'm going to take this number of matches between X and Y, and I'm going to take a regression on X and Y. So I can always do that. It's been done a lot. And then you do, I don't know if it's good English, it's a French idiom that you wet your finger to see where the wind comes from. It's a thing I learned in the military, so that's basically the kind of interpretation that you're going to do. It's not good, okay? So we don't really know what the coefficients mean. So here, this is how we are going to do it. So the first thing is that you have those mu hat. They come from a sample from the population, so they have a sampling variance. It's easy to compute, you know, things like mu hat multiplied by 1 minus mu hat, a bit more complicated. Then you use the delta method to compute the variance of twice the logarithm, and that's it. So you're just going to take the matrix of the explanatory variable, multiply by this thing here, or it's inverse, actually, I'm sorry, it's the inverse. Then by phi, and then you solve this linear system. So this is just a form of generalized least squares. So that's how we estimate it. Couldn't get much easier than that. And in addition, when you do least squares, you are minimizing something, so you can take the sum of the squared residuals, and the sum of squared residuals gives you an F-test. It's a test of specification. So if I didn't get wrong, so if the model is linear and I got the right basis of explanatory covariance phi, I just have to take this thing, norm it by the same S star, and I'm going to get a chi-square. So very easy to estimate, and we get a specification test in addition. Okay, and it's consistent, asymptotically normal. All right, so where does that come from? Well, I'm going to start to just take the simplest model, again, perfectly transferable utility, one-to-one bipartite, men and women getting married or not getting married. Some people could remain single, okay? All right, so then what do we have? We have the standard stability. I should really go fast on this. So we have the standard stability constraints that say that the sum of the equilibrium utilities have to be at least equal to what they would get by matching together. So phi MW is generated within a match by both the observed characteristics and the unobserved characteristics interacting. And there's equality, they do match because utility is perfectly transferable, so they're going to split to divide the surplus. Okay, all right. So we get this, an equilibrium, as we know, minimizes the sum of utilities, that's the dual, and the multipliers are going to be the 0, 1 matching indicators, whether M matches W, and the multipliers maximize the primal problem, and the multipliers here are going to be the UM and the VW. Okay, so we can use either of them. But now we do econometrics, so we need unobserved heterogeneity. So just like Choo and Siow did, we're going to say, well, the surplus comes partly from the observed characteristics of this man and that woman, and then there's some zeta MW. The problem with zeta MW is we do not observe it, and all we are going to have is whether these guys end up being matched or not, and we are going to observe the characteristics. So we know that even if you take a one-sided discrete choice model, you need strong assumptions or a lot of data in order to identify it and to estimate it. So here it's two-sided, so it gets a bit worse. There's squared the number of cells and the number of matches, so it's more complicated. And so we're going to restrict this zeta. And what we're going to do is essentially what I've written before. We're going to say, okay, there's a function. I don't know what it is. It depends on the observed characteristics. And then there is this one. All the characteristics of the man interacted with only the observed characteristics of the woman. And then there is the symmetric term. But we are not allowing M and W to interact conditional on the observed variables. So that doesn't mean there's no matching on unobservables. There is matching on unobservables because the men who tend to have a higher, within a particular age, who tend to have a higher taste for women with a Y are going to match with women who within Y tend to have a higher taste for the men of characteristics X. So they're still matching on unobservables, but we've restricted it. And the beauty about it is all these results, which are easy to prove, that said that basically you reduce the dimensionality of the problem. So a man M is just going to want to choose the observed characteristics of their partner. And so it's become a one-sided discrete choice problem. There's the same for women. Of course, I don't know the U, the capital U and the capital V, but they are much smaller dimension than the little um and the little w. I may have 10,000 men, 10,000 women, that's 20,000 things. But if they're only in 10 groups, I get 100 numbers, 200, but there's equality if there's so much. Okay, so once we have this, what do we do? So we want to specify a model. So we're going to choose a distribution for the epsilons. Again, so this is a man M, and he has specific shots. You can interpret them in a variety of ways, with women of different types, where 0, as usual, is not being matched. And then you can prove that this phi bar, remember, I have phi bar, I have the epsilons, I have the eta. I have chosen a distribution for epsilon. I have chosen a distribution for eta. All I have to estimate is the phi bar matrix. And so you get this closed form formula. I mean, to define things, but the generalized entropy function is essentially something that has to do with the value of matching on unobservables. And we called it the generalized entropy because in the Choo and Siow model, it's really the entropy. It's the standard entropy function. In general, it's a bit more complicated. So where does it come from? In a discrete choice model, the first thing you want to do is take the expectation of the maths you can get which is just your utility in equilibrium. So if you have this UHY determined, which we don't have yet, this is going to be the expectation of the maps. It's a convex function because this is linear, this is convex, and this is linear. So it's convex. So and we know, of course, that the probability of choosing one particular y, which is here, which is something we are going to observe in the data, is just the derivative of this function. Now, I don't know this, so it doesn't help me very much, except that convex functions are invertible. They are invertible in the sense of convex duality. So how do you realize this miracle? It's multidimensional, but you can, you can take the Legendre-Fenchel transform of G8. We know the Legendre-Fenchel transform is always a convex function. And in this case, since it's the transform of a convex function, its own transform is the function we started with, which is also nice because it helps us a lot. And this then is very important to us, but because it's telling us this G star its function is the transform of this function. This function, once I know the distribution of epsilon, because I postulated it, I can compute it. So I can compute this function. I observe this in the data. They're just matching probabilities. And so I'm going to get the U's. I can do the same with women, and I'm going to get the V's. And because U plus V is equal to phi bar, I'm going to get a phi bar that is the sum of derivatives like this, and that's going to be my generalized entropy. Okay, all right, so this is something like that. There's a bit of notation, but it's really very simple. So where do I go from here? Well, suppose I want to estimate the parameters of both things. The phi bar, which is the part of the joint surplus from a match that is generated by interaction between between observable characteristics. And I also want to give myself a bit of flexibility with the distributions. So I want to say epsilon as a distribution that depends on some parameters, which I want to estimate. And I want to also let eta have a distribution that has some parameters that I want to estimate. So what we have here is really what's called in statistics a mixed hypothesis. A mixed hypothesis just says, well, there's something that's really easy to estimate. It's the matching probabilities. I know how many white women with a college education married with a white man with a PhD, okay? So I know the mu, and I'm especially interested in the alpha and the beta, but they satisfy this equality. So what I can do is just take this. So this holds for every possible cell. And I can try to find the alpha and the beta that made this as close to possible as equal, sorry. And of course, there are disciplined ways of doing this. You have a vector of condition or a matrix of conditions, so you want to weigh them in the appropriate manner. That's why I had the S star originally. So we get mu hat from the data, and then we do this. So that's a minimum distance estimator. That's general formulation, and you find beta and alpha. Now, in addition, if you choose the weighting norm optimally, so which is simple to do, then you can look at the value of over the minimum. So you're minimizing the square of the difference, the weighted square for the right norm of the differences between phi beta and minus the derivative of the generalized entropy for alpha. And then when you get to the minimum, you're happy, you have an estimator of alpha, you have an estimator of beta. But in addition, the minimum, I should have said lambda is just putting alpha and beta together. The minimum is a chi-square under the null hypothesis of that the model is well specified. So you can test the model. Now, if you look at this, this is still this one. You can make it linear. Yes? Or much less than that? Thank you. So you might want to simplify this to make it linear. That would be great, right? Because if you minimize a weighted norm of this matrix, and this is linear in beta, and this is linear in alpha, then you're going to do a form of least squares, just like we did before in the Choo and Siow model. The Choo and Siow model, my first example, there's no alpha because we've said we have standardized the distribution, they're type 1 extreme values, so there's no alpha parameter. So this term is easy, no alpha here. And I also put this to be linear. So that's one thing we can do. It doesn't come very naturally for models that have the joint utility within a couple. Is generated because if you look at a couple, you're going to say, well, they choose their labor supplies, they choose their consumption, and they, they use maybe some household collective choice model. It's not easy to generate something that's linear in the parameters. But you could always say, okay, this is a sort of flexible specification. I'm going to put reasonable basis function, little phi xy, as I did before, multiplied by beta. Then once I have an estimator, I can take a structural model of what happens within the couple and estimate the nonlinear parameters. That's one way to do it. Now, this is a bit hand-waving as a justification for linearity in beta. This one actually is much better because the most common specification you can think of, they're actually linear in alpha. If you take, for instance, something like type 1 extreme value, but you allow it to be heteroscedastic, then this is going to be linear in the standard errors that come in the heteroscedastic specification. If you take a nested logit, it's also going to give you something linear. So this is pretty weak to get this linear, which really helps, because even if this is not, then you can maximize over alpha for a given beta, and then you just have to maximize over beta. So, like profiled estimation. Okay? All right, so this I already said. Now, again, linear in alpha means you can minimize the weighted norm. And if it's linear in beta, then you get what I gave you before, which was quasi-generalized least squares. So it couldn't really be much simpler. And I mean, it runs in, I have a Python package if you want it. And this kind of thing runs in less than 1 second, so much less. Okay? All right, so there are, as I said, you can apply these methods to imperfectly transferable utility. I was not going to talk about that, but since I have a few minutes, I'm going to. So this is not me. This is my co-author, Alfred Galichon, and Scott Cominers, and Simon Weber. And basically, all you have to do is you put an equation on the utility possibility frontier. So instead of saying the sum is constant, you put some equation there. Then you use a distance projection argument, and you're going to end up with something that looks very much like what I've done. Now, one way in which you have to be careful is if you start to say the utility possibility frontier does not only depend on the observed characteristics of the partners, but also on unobserved characteristics, then that's going to be more difficult. At a minimum, you don't want them to interact. But you can have, for instance, utility possibility frontiers that depend on X and Y. If you want to estimate them, well, that's additional parameters. It can be done, but you're going to need quite a bit of data. So we can do many-to-one matching, like the Kelso-Crawford model. At least we've done it with perfectly transferable utility. I haven't tried the other one. You can do multipartite matching, like a rugby team. Soccer team, I'm sorry. There's the World Cup of rugby, the Rugby World Cup in Paris at the moment. So you can do teams, for instance, teams in which people have different roles. You can do unipartite matching. So this is, we've decided not to call it roommate. Gale and Shapley called it roommate, but it sounds really strange at present. Nobody understands why. But unipartite matching is just you don't have these two populations separated ex ante, and anyone in the population can match anyone. So that's the easiest extension. Continuous characteristics are a bit more complicated because discrete choice models do not extend well. Did you have a question? No, sorry. So discrete choice models do not extend very easily to continuous choice model. Utilities go to infinity and so on. So you have to be a bit more specific about what you want to do. There is an easy extension, which is when you continue to use these Goombel, and you make them into the proper kind of Poisson process. So that works. Okay. And that's pretty much all I wanted to do. So if you're interested in matching with perfectly transferable utility or imperfectly transferable utility, I recommend that you look at these methods. We've gone a pretty long way from starting with, it was really difficult. And now it's actually a very easy task to estimate these models. So I think there will be more and more application. Thank you.
Thank you very much. There is a bit of time while maybe Attila sets up to ask a question if anybody has any question or comment. Everybody is super happy. Thank you again. Attila, the floor is yours.
Thank you.